series. Okay, so who's more active? Who wants to be part of the compound? Who is part of the compound? Ah.
No reaction.
No reaction takes place. Yeah. No. Activity series is supplied. Okay. Try one more.
But I noticed it.
I'm sorry? HCl. Okay.
Where's
What is wood pump? Gotcha. Yeah, it's an H.
oh. Oh, that was oh, sorry. Let's see, I get high five.
That's because you can always just fun.
No, it's because
Yeah.
Okay. Who's in competition? Magnesium and hydrogen. Who's more active? Who wants to be part of the compound? Who is part of the compound? Ah, so reaction must occur. So the magnesium is going to pair up with the chlorine. What's the charge on a magnesium? Chlorine. Correct formula. And why is it H2? It's a Hunkelbreath. So are we done?
That's what I told us in high school. It was Brinkelhoff. I remember it.
You're not in high school anymore.
2 here.
Neither are you.
All right.
Although sometimes you can fool me.
Hunkelbreath. Remember the term Hunkelbreath? Tells us the 7 elements that always occur as diatoms. And hydrogen is one of those, so it's H2 occurs.
Oh, nice. I'll be afraid of it. I'll be cautious.
Okay, so the question was asked, do you have to memorize the activity series? Of course not,
It'll be part of our data.
okay? It'll be part of the data. Or, is it possible that I could give you a question that dealt with the activity series without giving you the activity series and you're still able to answer it? Yes.
Yeah.
Let me give you such a question.
You have to tell us so. My feathers almost dead. Can you turn the projector off?
Not more of these.
No, just the word part. Okay, so given the reaction, zinc plus copper 2 nitrate reacts to form zinc nitrate plus copper, and silver plus copper 2 nitrate leads to no reaction. The question might be, what is the most active metal? Now, if you had an activity series, this would be easy, right?
Yeah.
You look on the activity series and find out which one was listed highest up. But there's no activity series up there. So we have to decide from the data that's given. How do we decide? Well, let's take them 2 at a time. Zinc and copper. What can we conclude about the activities of zinc and copper?
Zinc is higher than copper.
Zinc must be higher because the reaction takes place, zinc kicks the copper out. So wherever the activity series is, zinc must be higher than the copper. What does the second reaction tell me?
Copper is higher than silver.
Copper is higher than the silver because otherwise a reaction would have occurred. And so can we now state which is the most active metal?
Zinc.
Zinc, or at least I think so.
Ah.
Could you tell me the least active metal?
Silver.
Could you tell me the mediumest active metal?
Copper.
Yeah, you're right. All right, great. Okay, want to talk, put your pencils down. Because I want to talk about another type of chemical reaction. But this is a type of chemical reaction that isn't the type like we've been talking about. This is a totally different way to view chemical reactions. In fact, some of the reactions that we've already done are of this new type. And I don't want to spend a lot of time on this, and I'm not going to ask you any questions about it, and that's why I told you to put your pencils down. But I want you to have heard the terms, because some of you are going on to Chemistry 1152 next semester, and you're going to hear this particular reaction, and you should have heard something about it before. Now, unfortunately, what you hear there is not going to be the same thing that you hear here, okay? Because there are a couple of different ways of looking at this. What I'm talking about is a reaction that's called a redox reaction. The term redox comes from two words. It comes from the word reduction and the word oxidation. And these are two chemical processes that happen together. And so we combine their names together and we come up with redox. Here's the thing that you might want to remember, although it's not going to help you a lot. Oxidation is the loss of electrons. Therefore, reduction, an opposite process, becomes the gain of electrons. And these two processes must happen together. Now, why do we want to bother with this at all? If we were a more advanced class, if you were taking Chemistry 1211, for example, you would learn how to balance redox reactions. They are difficult reactions. You could spend 3 days trying to balance a redox reaction unless you know the steps. There's an outlined set of steps, kind of like what we did with dot structures. We had a set of steps to follow and gave us the right answer every time. There are a set of steps to follow for redox reactions, in which case you can balance even the most difficult redox reactions in a matter of just minutes if you follow the steps. We're not going to do that, but they are there. Now, can we show a redox reaction? Single replacement reactions are redox reactions. Because what's the charge on the magnesium right here? Oh, careful. It's neutral, it's 0. Magnesium metal has no charge. The +2 only comes about when the magnesium is involved in a compound. Okay? And so what's the charge on the magnesium here? Now it's +2. So look what's happened. It's gone from a 0 to a +2, which means it has lost 2 electrons. That's an oxidation process. The hydrogen, on the other hand, has gone from a +1 to a 0, which means it has gained electrons, and that's a reduction process. So the two always happen together in a balanced form. Now, next semester, oxidation reactions are a considerably big part of Chemistry 1152. But you won't be doing this in terms of electrons. You'll be doing it in terms of organic chemistry. And there are shortcuts to take. And so that's why I don't think it's worth our time to spend any time on it now. But you'll have heard the term. And when your organic instructor says, we're going to talk about an oxidation reaction, you could yell out, that's a loss of electrons. And they'll be so impressed with you. But they'll probably give you extra points. Okay. We're not going to do anything with it. So what are we going to do? How about we try a few reactions? And we'll see how well we are at balancing these reactions. So maybe we should try the first 5. Okay, go. Done. Did you start in the middle?
Huh?
Did you start? Oh, here. Oh, that's right. Okay. Good. This one, remember, think of water as H-O-N. And see the difference in these things. Okay, it's not incorrect. But it's not. This is not bad, but it's better if you think of water as H-O-N. Done? This is not in, but it would be better if you thought water was
I have no idea what.
That's good. That's that. That's that. Got to write correct. And the form is first. And then that's your first job. And what's it take down? Then you got this. This is totally correct. This is totally only applies when it's long. It's a long day. And it's have two. And now we-
Why is this little chart relative? Like, are we supposed to use that or? The chart? What do you do?
So I'll read it to like the NaHCO3.
Oh no, because that's double replacement. The chart isn't really needed.
What do I need?
You need the chart for single replacement.
So they'll do this right?
You have 2HF and then 2H3.
It's too many. You have 2H3 and 4H3.
I have a question on that.
What's wrong?
What's a C2? You have N2 and H2.
Oh, well,
It's gonna make HN and nitrogen minus 3 hydrogens plus 1.
right?
So you need HN3. H3N,
Mhm.
right?
I have that.
And then you have
So the chart on hydroxide is minus
3 hydrogens here and 2 hydrogens here, a common factor of 6. So I put a 2 here and a 3 here. So we have 6 hydrogens on each side and 2 nitrogens on each side.
I need this.
Oh, wow.
You overdid yourself.
I did. Okay, so it should be equals NA2. Oh, so you just do the common factors. It makes life a whole lot easier.
Not factors, products.
Common products, okay.
Whatever.
When I
Call
did
it.
do it originally,
I think it's the greatest common factor, the GCF or something like that.
You don't do the greatest. It's
The least.
and that's what I said. Have you done the last one? I'm just confused.
it is confusing me.
Because I
Sodium bicarbonate, aren't these both compounds?
and then you have HHCO3.
Isn't that a compound? Isn't that hydrogen?
Huh?
Isn't that hydrogen chloride? Use sodium bicarbonate with hydrogen chloride.
When you mix sodium bicarbonate and hydrogen chloride, I got NaCl, and then I got HCO3.
You did? Because sodium is higher than hydrogen.
But I don't think you do that in a double reaction.
Is that a real?
Yeah, that's a double replacement.
The ones that
I'm confused.
I need the
Um. Going this way for it to be a noble gas.
Aluminum.
Yes. Because it's right there. And you go, why don't you?
Oh, I guess it's me.
Yeah. Well, no, it wouldn't. It's yeah, it would be yeah. And then bring the link to the
C.
Yeah, or the sun more.
Yeah, I think you only use the chart for a single replacement because that's deciding which one is going to be a part of it.
Oh, the last one is a double.
Yeah, it's just weird. It's like HHCO3. I think it's one of those things that doesn't make yeah, it was one of the things that doesn't make sense in our brain, but it does in chemistry. I don't know. That's the question I was gonna ask him, but he's
It will.
helping.
It will. Most people won't know that.
Maybe he's not anymore.
See the CO3?
Yeah.
Put another H on there.
Yeah.
And then it should be CO3. That's it. You go to the calculation, give you CO2 as well. That's why. Yeah. I'll be right back. First one is
She's like, I'm still trying to understand.
I'm sorry, no, I'm still trying to tell what.
So is mine.
I got
Tommy wings. You can cut it into like a salad.
I like
Tommy.
Are you gonna change that to pearls, or are you gonna get the same hairstyle you have now?
It's gonna be
You're trying to balance yourself.
Well, I understand.
I understand. We understand. Yeah, I know. I understand. I know you don't, because I who I went to school with.
My roommates talked to me about that, like Brazilian bees.
The what?
That's what they do. They're like, the Brazilian bees is the best bees to put in my hair. And I was like, why? And they said, it's just really pretty and curly, and the textures, yeah, the texture's the best. And it's, I'm just like, okay.
Yeah. She gets a Brazilian hair done. You should let them do your hair.
No, I don't need weave.
They can do your hair like cornrows.
Yeah.
Like you put both in your hair.
Yeah,
I don't
but
wash their hair all the time.
my roommate Diaper said it smells. Like after a while, the weed.
Every day. Every day. It's things when you buy it, yeah. But then you wash it. Yeah, make it sound good.
No.
Yeah, they have to wash their hair.
I wash my hair every other day.
They don't do that. They don't do that. Don't mess up my hair. I don't know that. Didn't know that.
I'm kind of jelly because I have to fix my hair every day.
That's why we're not going for lights. Lights is most of the
I wish I had done that in middle school.
You can write it as H2
That's not true.
or
That is not
HHCO3.
true.
The last one.
Okay. That is true.
Or you could write it as H2.
Do you accept both?
I will accept that.
Dr. Ron, when is this chart supposed to be used? Is that for single
Single replacement.
only?
Yeah.
Okay.
Yeah. I think they like our hair double, right?
Maybe I should.
We have reasons on this.
All right, let's try it.
More adults than have lights. We have 4 years.
We use green, it's a softer color, better for the ego. So in the first case, we have H2 plus F2, and we're told direct combination. So what is that clue giving us? That there's only one product. So the product has to be something that's made from hydrogen and fluorine. So in a compound, hydrogen would be a what? Plus 1. Fluorine? Minus 1. So the correct combination? HF. So we write HF first. Now our second job is to balance. So is it balanced?
No.
You need 2 in front of the HF. Okay. Second one, direct combination again, N2 plus H2. So we know that we have to write a compound made from nitrogen and hydrogen. Hydrogen would be a plus 1. Nitrogen?
-3.
Minus 3. So if I've got a plus 1 and a minus 3, what would the correct formula be? H3N, or NH3 is the way it's customarily written, incorrectly, but customary. But we can write H3N, that's perfectly acceptable. And then, since we've done our first job, writing the correct chemical formula, what's our second job?
Balance.
To balance. And so what would we do to balance this? We need a 3 here and a 2 here.
Does it matter which way you write it? You write NH3?
Yeah, you can write NH3. I'll take that. Okay, Na plus H2O. What type of reaction is this? Single replacement. Okay, element and a compound. It's probably better if you think of this as HOH. So I would mostly get in the habit of, if you see H2O, rewrite it right above it as HOH right away. Now, single replacement. So who's in competition here? Sodium and hydrogen. So there's an activity series over there. Who's more active? Who wants to be part of the compound? Who is part of the compound? So there's going to be an exchange that takes place. So the sodium is going to pair up with the who? The hydroxide. That's why we want to write it as HOH, is because it's really going to pair up with the hydroxide. And sodium is a plus 1, hydroxide minus 1, so it makes NaOH, and it leaves hydrogen alone, which is H2, because of the Hankel-Briff connection. Okay. We've got correct chemical formulas. Yes, sir.
This on the second one. 3H2 N2, correct?
No. No, that would be wrong. Because nitrogen's a minus 3, hydrogen's a plus 1. So if you only put 2 hydrogens on there, you wouldn't have a neutral compound.
What are we wrong with nitrogen?
No, you can put the NH3, that's fine. All right, so on our third one, are we balanced? Yes, ma'am.
Say that this question was on the same, like, and I wrote it out differently, would it be wrong if I didn't have it like that?
Well, I don't know. Tell me what your differently is.
Well, in my more complicated, 2 NA plus H2O. Oh, you know.
I'm waiting for you to tell me what it is.
Yes, I'm saying. I'll tell you my product.
All right. 2 H2O
Yeah, no, 1 H2O.
plus H2O.
And I got H2 plus Na2O.
That's acceptable, okay? The problem is that's not what happens. That's what we would think happens looking at this. And that's why I tell you, don't think of this as hydrogen and oxide. Think of this as hydrogen and hydroxide. because that's the way the water almost always reacts. So even though this is correct on paper, in the laboratory, this is the answer that we get, except that this is not balanced. So, balancing? We're good?
Yes.
Okay. Then we have aluminum plus HCl. Type of reaction. Single replacement again. We have to consult the activity series. Who's the competition between? Aluminum hydrogen, who's more active? Who wants to be part of the compound? Who is part of the compound? So reaction occurs. So I have to pair aluminum up with chlorine. In a compound, what's the charge on aluminum going to be? Plus 3. Chlorine? -1. So correct formula? And then it leaves hydrogen alone. So I've done my first job, writing correct chemical formulas. Second job, cool. Okay, what type of reaction do I have? Double replacement, because it's 2 compounds. And what happens in double replacement? They're swingers, they're switching partners, right? So the sodium is going to pair up with the who? The chlorine. What's the charge on a sodium? Chlorine. Correct formula.
I guess it could flow the other way.
What's the other pairing? Hydrogen's pairing up with the bicarbonate. What's the charge on a hydrogen? Charge on a bicarbonate. Correct combination. HHCO3, or I could write it as H2CO3. Now in truth, what happens here is the H2CO3 undergoes a decomposition reaction to form water and carbon dioxide. And so you get a bubbling to take place, an effervescence, because of the carbon dioxide gas given off. There is probably no way you would know that. So we would expect you to end with the H2CO3 as your product for the reaction. All right? Questions?
How do you get for the fourth problem? I'm confused. How do we get the 2 and the 6?
Well, let's go back to where we have nothing here and try to balance it. So I'll start with aluminum. How many aluminums here? How many here?
1.
They look okay. Hydrogens.
1. 2.
So I might need a 2 there. Okay. Chlorines.
2.
3.
Oh, it's,
There's 2 here,
oh, okay, 2.
but there's 3 here.
3.
So I need more here. Why don't I make that a 3? Okay. So now let me go back and check to make sure I didn't knock anything else out of balance. Aluminums,
1.
hydrogens,
3.
need more here. Let's put a 2. Hydrogens,
4.
Oh, 4.
4. So I better put a 4 here. It's exhausting. Chlorines,
4.
3.
It's only 3.
So I need more here. I better put a 2 here. So now let me go back and start over again. Aluminum.
1. You need to balance with 2.
Okay. Hydrogens.
There are 4. 2. 4. Oh, 4. 4.
Chlorines.
And there are
4 and 6.
4.
6.
6. So
I need 6.
hydrogens.
4.
Hold on.
6 and 6.
Okay.
Okay.
Okay. A chemical reaction actually gives us a lot of information. At this point, we know that it certainly tells us who the components are for both reactants and products. And it also, if we think about it, tells us something about the amounts of these guys. How many reactants and how many products I have when I write a balanced reaction. So now that we have that, we can start putting that to our advantage and start doing some investigations and some calculations. For example, one question that might come up is, how much of one substance will react with how much of another substance to create a certain amount of product? This process that we're talking about has a name, and it's called stoichiometry. Crazy word. It means to count piled stones. What the hell that has to do with balancing chemical reactions, I don't know. But it's the term we use to talk about these mathematical relationships that we have. Now, the first thing you need to do any kind of stoichiometry problem is a balanced chemical reaction. We cannot do anything without a correctly balanced chemical reaction. And by now you know that means A, first job, correct chemical formulas. Second job, balance it correctly. Okay? So we're going to start out with a simple one. Let's take hydrogen and chlorine to make HCl, hydrogen chloride. Am I balanced?
No.
So I need a 2 here in order to get the balanced chemical reaction. Now, if you think about it, this chemical reaction is very similar to a recipe. It tells me that if I go into the laboratory and I take 1 mole of hydrogen, because without a coefficient there's a 1 there, so that means 1 mole of hydrogen, and I react it with 1 mole of chlorine, waka waka waka, I make 2 moles of HCl. That's just like a recipe. Think of a recipe that you have at home. Everybody has a recipe for chocolate chip cookies, right?
Yeah.
We love chocolate chip cookies. Don't have a recipe for chocolate.
Kroger. Put it in the oven.
All right. Most of us have a recipe for chocolate chip cookies. Let's talk about that recipe for chocolate chip cookies. What are some of the reactants, in other words, the ingredients that are in there? Eggs, flour, sugar, chocolate chips. How much? A little bit of baking powder.
Vanilla extract.
Vanilla extract, brown sugar. Okay, we got a lot of ingredients, right? Now, it's not enough to just list the ingredients.
Gotta combine them.
Not only combine them, but we have to know how much of each ingredient. So, flour. How much flour?
1 cup.
No, it's way more.
Not near enough to feed the class. Now, we're talking.
Now we're talking 4 cups.
Okay, 4 cups. Cups of flour. Eggs. How many eggs?
3.
3.
You see, we're talking whole numbers of eggs, right? Not cups. How much baking powder?
It's about half a teaspoon.
half a teaspoon, quarter teaspoon. Sugar.
Lots of sugar.
Brown sugar though.
Yeah, we have to
Brown
probably
sugar.
a cup of brown sugar.
About a cup.
So cups again.
Yeah.
Chips.
About 2
Bags, right? We're talking bags of chips. Can't wait for those. All right. Notice the difficulty here. Now, we're all familiar with recipes. We're all familiar with chocolate chips. But think of the complexity in this. You've got all these ingredients, and almost every one of them has a different type of measuring value for it. Whole numbers for eggs, cups for flour and the sugar, quarter teaspoon for the baking powder, soda, whatever, bags for the chips. Okay? What's the great thing about the chemical recipe? The unit is always the same.
One.
It's always measured in moles. Everything is in terms of moles. 1 mole of hydrogen, 1 mole of chlorine produces 2 moles of HCl. Everything is done in moles. It's simplified for us. So stoichiometry begins to be as simpler than baking chocolate chip cookies, which we've all tried to do, or maybe cheated. But we get the idea. Okay, now when I go into the laboratory, do I have to do this reaction with 1 mole of hydrogen? No. Just like my chocolate chip cookies, I didn't have to use 1 cup of flour. If we're making for the entire class, we need more. 4 cups of flour, maybe more. 10 pounds of flour, possibly. Okay? We're going to make it for the entire class. 10 pounds of flour, let's say. So, can I cut my recipe down? Could I use a half a mole of hydrogen? And I would make less HCl. Now, chocolate chip cookies, could I make a double batch? Could I make a half a batch? Theoretically, if I wanted to, and I was on a very strict diet, could I make 1 chocolate chip cookie? It'd be tough. Well, you can. You can break the egg in a bowl and take only half of it or whatever, but it's not going to be easy, but you could theoretically make 1 chocolate chip cookie. Or put all the ingredients in there, make 1 big one, and tell yourself it's only 1. Okay? That'll work too. Okay, so what's the deal here? We can change the amounts. And when we change the amounts of everything. Yes? Oh, just stretching. So, I don't have to use 1 mole of hydrogen. Could I go into the lab and say, I'm going to do this reaction, and I'm going to use 2 moles of hydrogen? Then how much chlorine would I need? It's obvious, right? It's a 1-to-1 ratio between the two. If I use 2 moles of hydrogen, I've got to use 2 moles of chlorine.
Don't you always have 2 moles of it since it's in alcohol?
No. No. I have only 1 mole of hydrogen. The hydrogen comes as H2, but it's 1 mole of H2.
Oh.
But I can elect to use 2 moles. Now, what I want to do is to show you the calculation that we would do to actually get 2 moles of chlorine. There's no question in here. Everybody's thinking, all right, I need 2 moles of chlorine to react this with 2 moles of hydrogen. But why is that the case? If we understand the mathematics for this simple case of 2 moles of hydrogen, then if we change the numbers in either the balanced chemical equation or the amounts that we use, it shouldn't be a problem. If we know the process is the same, all we have to do is change the numbers. So, this is very much like conversions. We start off with what we know. 2 moles of hydrogen. And what I'm doing is I'm looking for a conversion factor that's going to change hydrogen into chlorine. Because I know hydrogen, my question is, how much chlorine do I need? So, I set up a conversion factor of what I'm looking for, moles of chlorine, compared to what I know, moles of hydrogen. And the conversion factor is always in this form. What I'm looking for over what I already know. Now, the question is, what's the connection? What is that conversion factor? That always comes, how often? Always comes from the balanced chemical reaction. So all I have to do is look up here and say, how does chlorine relate to hydrogen? Oh, it's a 1-to-1. Look what happens. Moles of hydrogen cancel. I'm left with an answer that says moles of chlorine, and mathematically it would be 2 moles of chlorine, which is exactly what you told me. That's how I would get it. Now, if I take a tougher equation that doesn't have 1-to-1 ratio, it's not a problem, because what will that do? All that will do is change these numbers. And if I have a calculator, can I still do this calculation with changed numbers here? Yeah. I'll answer for you. Yes. That's how much I started with. That was just a random amount to start with. I said I'm going into the lab and I want to do this with 2 moles of H2. I could have picked any amount. I could pick 3.7. If I picked 3.7 moles of H2 to start with, how much chlorine would I have used? 3.7, because it's a 1-to-1 mole ratio. Now, I can relate one thing, like the hydrogen, to anything in the equation. It doesn't have to be another reactant. It could be anything. It could be the product. In other words, if you're making your chocolate chip recipe at home, how many cookies does it make? Say 24. 24. What if you double that recipe?
48.
Then you could make 48. So you immediately know that if you double the ingredients, you get twice the amount of product. So I can find out how much HCl I'm going to make by the same type of calculation. Except this time I'm looking for HCl. And I know hydrogen. Now, what's the ratio between those two guys? 2-to-1. Where did you get that from?
The chemical reaction.
From the balanced chemical equation. Those numbers always come from the balanced chemical equation. So, 2 moles of HCl for 1 mole of hydrogen, because there's a 2 here and a 1 here. Moles of hydrogen cancel, and I'm left with, I should make 4 moles of HCl.
Where did you get your soup from?
What 2? This 2? From the balanced chemical equation. Always, they are the coefficients in the balanced chemical equation. Sure, but this is stoichiometry. If you understand what we've done here, then there's nothing to fear in terms of stoichiometry.
What's the definition of that?
The only thing that changes is the numbers.
The seal.
Stoichiometry is the relationship between the quantities of substances in a chemical reaction. Okay. Literally, it means to count piled stones. Why? I don't know. Good question. Extra. No. No, don't go there. Good extra question, extra credit question for the test, though. I put on there occasionally spell stoichiometry.
Do you really?
Yeah. Realize it's printed on the test, spell stoichiometry. Every time I've done it, I've had at least 2 people miss it. Stuff in the reaction. Okay. Now, can I complicate the problem? Of course. It's what we do best in chemistry, right? Is we complicate things. How could I complicate the problem? I started out with moles. But if I go into the laboratory, I'm not likely to weigh something out in moles because I don't have a mole balance. But I'm going to do it in grams. Now, if I gave you a gram amount, could we still do the problem? Yes, but what would be our first step? Convert to moles. This is one of those golden rule types of things, right? That you're going to get tattooed on your arm if you don't have it already. Convert to moles. So if I'm given some gram amount, the first thing I'm going to do is convert to moles. This relationship, this connection from one substance to another substance always has to be done in terms of moles. Now I'm going to get an answer in moles, but if I wanted an answer in grams, could I change moles to grams?
Yeah.
We know how to do that. We know how to change grams to moles and moles to grams. That was on the first exam. We looked at that a long time ago, and we can handle that kind of problem. So, what if I had said to you, you have 10 grams of hydrogen. How much chlorine is needed? Okay. Oh, this is a different problem now. Doesn't say, does it? And so we'll talk about that. That's an excellent observation. So let's start. 10 grams of hydrogen. Grams does me no good. What do I want to do? Convert it to moles.
Using the same equation.
Yeah, for the moment. So I have 10 grams of hydrogen. How do I change that to moles? Yes, ma'am.
You look at the hydrogen, whatever.
Atomic weight in the periodic table?
Yeah.
I knew that's what you were trying to say.
1.01 over 1.
Are you sure?
1.008, but
Zero something.
Are you sure?
Yeah, over 1 mole of H2, and then you go to your.
Twice that big?
It should be twice that amount because it's not H, it's H2. And remember, when you have a formula, you have to add all the atomic masses for all the atoms present. So this would be 1 mole of hydrogen for every 2 grams of hydrogen.
And then you just go to your.
And so now grams cancel, and I'm left with 5 moles of hydrogen.
Well, then what are you asking for?
Let's go back and see. Oh, here's the question mark. How much chlorine is needed? So what do I want to do now? I want to relate the amount of hydrogen to the amount of chlorine. So I'm going to say, well, I'm really looking for chlorine. I know hydrogen. What's the connection between those two guys? Where'd you find that? Balanced chemical equation, 1 to 1. So my answer is 5 moles of chlorine.
How did you know looking for moles?
I didn't. I was asked how much. Now, is a mole answer an answer to the question how much? I think it is. And I would stop here. Why? I could. I would stop here because A, I'm looking for time, to save time on the test. Why should I do an extra calculation if I don't have to? And B, every time you do an extra calculation, what's the chance of something happening? You can make a mistake, right? So I would leave it as moles. Now, if the question said how many grams of chlorine, now I've got no choice. I have another step to do. And so how would I do that? What would I multiply what?
35.45.
Excellent guess. It's wrong, but an excellent guess. Times 2. So 71 grams for 1 mole of Cl2. Okay? And that's, 355 grams of chlorine. So I can stop at moles if I'm given that option, or I can go all the way to grams if I need to get that option. Yes, ma'am.
so will there always be a balance?
Excellent question. On the exam,
Bless you.
I will always give you the balanced equation. Why? In order to do the stoichiometry correctly, you need a correctly balanced chemical equation. If I'm going to give this to you on an exam and I want you to balance the equation, I might have to work out 60 different stoichiometry problems because you could possibly balance it differently every person, right? And I'm certainly going to grade your result on how you balance the equation to see if you did the stoichiometry correctly. So to avoid that possibility of a lot of work for me, since I'm basically a lazy guy, I will give you the balanced equation, which means everybody should have the same coefficients. Now, homework problems are not as nice as your instructor. Homework problems will give you an equation and expect you to balance it correctly first before you do the stoichiometry. But on the exam, I'll give you the stoichiometric problem, I'll give you the balanced equation. Yes, it is. It is straight away conversion all over again.
I don't like it. Are there any practice problems?
There are practice problems on the website, a whole sheet of them.
So you're saying on the test, you're gonna give us the balanced equation, or you just do this right
I am giving you the balanced equation for the stoichiometry problem. Most people will not agree with you. Now, can I complicate the problem further?
Yes, you can.
Yes, I can. How is that going to happen? Well, let's take a real life scenario. Okay? Let's say you decided to withdraw from school. Things aren't going as well as you thought. You thought you'd be understanding chemistry a little better. You're not. So you quit school and you get a job in an automobile factory. Okay? And you are put in charge of tires. You have a bin behind you that houses the tires. The bodies of the cars come rolling down the assembly line. They stop at you. You're the last step. And what do? You put 4 tires onto the car, and from you, it rolls into the showroom. Okay? Got the scenario? You're the last step. You're the tire guy. Goes from you into the showroom. So, the manager, a friend of yours who quit school a year ago, comes out and says, how many cars can we produce today? And you look behind you, and in your bin back here, you have 32 tires. You with me? Oh, you guys are sharp. 32 tires. So what do you tell the manager? 8 cars. Why? What happens after 8 cars? We're out of tires. We cannot produce anymore, right? Now, a friend of yours who quit school at the same time is in charge of bodies on the line. And the manager goes to that friend and says, how many cars can we produce today? And there's 10 bodies on the line. So what does your friend say? 10. The manager goes into the showroom and tells him how many cars to expect. What's his answer? 8. Because even though there's 10 bodies, once we outfit 8 of them, production stops. We call the tires the limiting reagent. And this is something that happens in chemistry all the time. If we put 2 chemicals together, what are the chances that they're going to react with each other exactly in those amounts? It's not good. Very small. So what's likely is something is going to run out first. And when it runs out first, the production of the product has to stop. And we have limited the reaction from taking place. So, how do we handle a limiting reagent problem? It's very simple. It's exactly what the manager did. What did the manager do to be able to tell the showroom the correct number of cars? He checked with you and the body guy. Because what if there had been only 5 bodies on the line? Then we could have only produced 5 cars and you would have extra tires in your bin, right? So, he checked with both and found out which number. Which number did he use? The smallest, the lowest number. Okay? That's exactly what we're going to do in this problem. We're going to calculate the amount of product twice. So, here's the job. We have 10 grams of hydrogen. And we have 71 grams of chlorine. Right? And we're mixing them together. And the question is, how much HCl can I produce? Can I declare what the limiting reagent is here?
No. Yes. No.
I cannot. You're tempted to say what? Hydrogen. Why? Because it's a smaller amount. But that smaller amount is in grams. And that is not how chemical substances react. They react in terms of moles. But even if you had the mole answer, you can't be sure you got the right guy with the smaller amount. Because let's go back to the factory. What's smaller? 10 bodies or 32 tires? 10 bodies is smaller number.
But which one runs out first? The tires, because it was a 4-to-1 ratio. So you see what I have to do here to get the correct answer is I have to go all the way. I have to calculate how much HCl can I make from 10 grams of hydrogen. Second step, how much HCl can I make from 71 grams of chlorine? Answer, smaller of the two. So I would do exactly what I did a second ago. 10 grams of hydrogen times 1 mole of hydrogen is 2 grams, giving me 5 moles of hydrogen, and I can make 2 moles of HCl every 1 mole of hydrogen. You already had this in your notes. This is what we did a second ago. Okay? So this is 10 moles of HCl. Voila, there's our first step, which is what we did a second ago earlier because we used 10 grams of hydrogen. So let this sit for a minute and we'll consider the second step. What's the second step? How much HCl can I make from 71 grams of chlorine? So I start with 71 grams of chlorine. What's my first step going to be? Convert it to moles. Golden rule, right? Convert to moles. How do I do that? Well, I need to know what 1 mole of chlorine weighs. 71. Because it's Cl2. So I take my 35.5 and I double it. Oh, what a coincidence that is. Look at that. I get 1 mole of chlorine. Now, what do I want to know? How much HCl? So I'm looking for HCl. I know chlorine. Well, if only I had a relationship between those two guys. Is it? It's 2-to-1. How do I know that? I look at the balanced chemical reaction to get those numbers, and this tells me that I can make 2 moles of HCl. So in truth, how much HCl can I make? 2 moles. Not 12. What happens? On the test I get half a dozen people who will add them together. Does that make any sense? No. It's got to be the smallest. So I would do something like put it in a box and say, this is my answer, so that you don't leave both of them there and I'm taken off because you haven't indicated an answer to the question. Okay? Now, how much HCl? Am I wise to stop at moles? Yeah. What if it said how many grams of HCl? Damn. I would still do these 2 steps in moles because I can compare the mole values easily enough. No need for me to turn both of them into grams. But then once I got this mole value as the final answer, I would then change that to grams. And how would I do that? 1 mole of HCl is I'll do it. I'm the only guy here. So we get about 73 grams of
Where'd you
HCl.
get the 36.5?
HCl. Chlorine is 35.5, hydrogen is 1.0. I added them together in my head without a calculator.
Wow.
Yes, it's true.
You got calculator for a brain.
There you go. Little gray cells snap to attention when I talk to them. And then I forget my wife's anniversary.
Your wife's
I know, right?
anniversary?
Yeah,
It's not your guys'?
happens to be mine too. Yes, ma'am.
This would only be if we need to take it to grams.
If you were asked to go to grams, then you would want to go to grams.
2 moles.
If you want to leave the answer in moles, then you can leave the answer in moles. That's perfectly all right.
It's possible. Depends on my mood or when I steal a problem from a textbook or something. What it says is what I put down. We're good? So are we stopping?
This is a no.
All right, we'll stop today if you promise me you're gonna